Hello everyone, my name is Rohan Javeri. I'm a student at CSU pursuing my masters in electrical and computer engineering, and today I'm going to briefly discuss about code compression techniques for low power embedded systems. The rapid growth in the technology, especially in the field of embedded systems, has increased the demand for faster processors. Also, the number of cores in the embedded systems have increased in order to perform multitasking and to improve the performance. But this increases memory access and number of bus cycles, which leads to increase in power consumption. As we all know that power is one of the major constraints in embedded system technology today, and memory access and bus cycles are the major reasons which leads to increase the power consumption. In order to decrease memory access, code compression techniques has proved to be very effective. The basic principle of code compression is to merge multiple instructions into one single instruction and store it in a separate database. Initially, a new instruction is read from the code file and checked whether it exists in the database. If the instruction exists in the database, the counter of the instruction is incremented by 1, and if it does not exist in the database, the instruction is added to it and the counter is set to 1. This process continues till the end of the program file is reached. Once the end of the file is reached, it replaces the instructions with the code word, which is basically the index to the instructions in the database. This is known as dictionary-based code compression technique. When the file is executed, the code words are being mapped to their instructions in the dictionary. This is known as decompression, and the process is exactly opposite as code compression. The dictionary-based code compression technique, as discussed in the previous section, is one of the most earliest and most used technique, but it takes into account only static instruction compression. In order to consider dynamic instructions, a variant of that technique known as two-level dictionary approach is implemented. It basically has two dictionaries. One is for single instructions, while other is for sequence of instructions varying from 2 to 16. While execution, the program comes across three cases. If the instruction is uncompressed, it directly executes it. If during execution it comes across a code word which has a single instruction, it goes to that specific dictionary and fetches that instruction. And if it comes across a code word which points to a dictionary which contains a sequence of instruction, then it goes to the dictionary containing sequence of instruction, which would map it to the other dictionary which has single instructions, and those instructions would be executed. But this technique gives good results only for dynamic instructions compression and not for static. Hence, to overcome this, multi-profile based code compression technique is developed. In this technique, a dictionary is created known as a unified dictionary, which is basically a blend of static instruction profile and dynamic instruction profile. It also has a provision for branch instruction, provided that the branch offset is small. It stores the 10 most significant bits of the branch offset inside the dictionary. Once the dictionary is created, the first instruction inside the dictionary is considered, and the compiler tries to build a COM packet. COM packet is basically a 32-bit code word which is used for compression. The figure below shows the different types of COM packet. This technique provides a compression ratio of 70% with a power improvement of 46%, and hence is very widely used. This is another code compression technique which is widely used in embedded systems. It is based on Hamming distance. Hamming distance is defined as the distance from the original vector. That is, the number of bits that differ from the original vector. In this scheme, the program vectors that are supposed to be selected should be at the most specified Hamming distance away from the dictionary vector. It also includes bit toggling information in order to decompress the program vector. This algorithm consists of 4 steps. The first step is known as the first input part, in which a dictionary is made from the instructions and is converted into a vector form. The second step is known as the first dictionary pass. In this step, the vector formed in the previous step are selected to form a reduced dictionary. The selection method is based on maximum frequency, in which the instructions that occur most frequently in the program are selected. Another selection method is called as the maximum span, in which the Hamming distance of the instruction is found out and the instruction that spans the most is selected. And the third selection method is a combination of both. The third step is known as the second dictionary pass. In this, the reduced dictionary is filled with the most frequent vectors from the original dictionary which are not included in the reduced dictionary. Due to this, the bit toggling is reduced even further, which should help to save power. The fourth and the final step is known as the final input pass, in which the vectors are converted into a code word. Another technique for code compression is the NOP compression scheme. NOP stands for no operation, and this instruction is used by the processors when it is required not to change any memory content or for byte alignment. but these instructions increases the number of cycles and thus the power consumption. Hence, for power constrained embedded systems, it is necessary to compress these instructions. In order to compress these instructions, we use a coarse-grained architecture which has a stop bit, which indicates whether the next instruction should be continued in the same cycle or not. Multiple instructions in the same cycle are known as NOP bundles. In NOP compression scheme, the processors use a queue which fetches the next instruction in advance, but this increases the possibility of cache miss because of the jump statements. In order to avoid this, we use a VLIW architecture, which uses a early compression technique. It has four types of early compression techniques. The first one is known as the no compression first bundle, in which the first bundle of all building blocks are not compressed. The second is the merge compression, in which if the compression bit of the first two bundles are same, then we merge them into the previous building blocks. Next is the super block, in which we compress only the not taken part, where that is the part which does not have branch predictions of the basic blocks. The fourth and the final technique is the branch hinted. In this we compress the both taken and non-taken part. This technique gives a compression ratio of 23%. Another code compression technique is the arithmetic coding technique, which is designed with the aim to reduce power by reducing the bit toggling. The algorithm is based on quasi-arithmetic coding and it makes use of the Markov model. The Markov process is shown below. It makes use of regular assignment and inverse assignment techniques to reduce the bit toggle. The rule of exchange of assignment states that if the Markov model and machine 1 tells that the next most probable output symbol will be 1 using the regular assignment and the previous word is 0 at the same position, then the encoder will switch to inverse assignment. Similarly, if the next highest probable transition will generate a 0 and the corresponding bit in the previous word is 1, the encoder will switch assignment. Based on this exchange rule, an expanded state graph is made, which is used for decompression and it is stored in a compressed form in the ROM. This method gives us a power consumption optimization by 35%, and hence it is widely used in embedded systems. Another technique for code compression is context-based adaptive binary arithmetic coding, which is just an extension of the normal arithmetic coding. It consists of 3 steps. The first step is binarization, in which it converts all the syntax elements into a stream of binary elements. The next step is known as context modeling, in which all the binary symbols are given a probability model, and depending on which they are modeled into different types of contexts. And the final step is the binary arithmetic coding as described in the previous section. In order to improve the power consumption further, a post-cache architecture is used which increases the cache hit ratio. When a cache hit occurs, the processor checks whether at least one instruction in the block is compressed or not, and it accordingly selects the instruction and sends it to the cache output line. In case of a cache miss, a miss handler is invoked and it fetches the requested block from the program memory to the cache. Once the block is transferred to the cache, the task that takes place in case of cache hit would be implemented. The last technique that I would like to discuss is compressed RAM for embedded systems. As discussed earlier, memory is one of the major constraints in embedded systems and is one of the major sources of power consumptions. So in order to reduce the power consumption, memory should be compressed. In this technique, we divide the RAM into 2 areas, namely compressed area and the working area. When the memory is low, it swaps out the pages from the working area to the compressed area, and in order to accommodate new pages. The pages which are swapped out are currently not in use or are very old. Hence the size of the RAM changes dynamically. The figure shown below describes the entire algorithm of compressed RAMs. Towards this end, I would like to say that code compression is relatively a new area which has started finding its roots in the embedded system technology. The various techniques discussed have proved to be very efficient to provide code compression at design time, but due to rapid development of technology and platform independent nature of new applications, there is a need for further development of technology and reduction in power consumption. This is leading to development of compiler techniques for code compression during runtime. Also, researchers are developing next-gen embedded systems which would perform cloud computing to reduce memory access and optimize power.